Hi budding engineers, welcome to Structural Engineering Lectures and welcome to the new playlist on the design of steel structures, limited method IS 800 2007. In today's class we shall see the design of eccentric welded connections, right? Wherein we'll see the design of unstiffened welded connection like this, right? Wherein only we'll see the design of the angle, just seat angle, as well as design of stiffened welded connection, right? Wherein we'll see the design of seat plate as well as stiffener plate like this, right? Seat plate as well as stiffener plate, right? That is how these two designs we'll see. Whereas in the previous class we have seen the designs of eccentrically loaded welded joints. That is how the bracket type 1 connection as well as type 2 bracket connection, right? I hope you enjoyed the discussions. If you enjoyed the discussion, don't forget to click like, comment, share, subscribe to our YouTube channel, right? Now let us move quickly to the top of the brief profile of the speaker. That is mine. I, Dr. D. Rupesh Kumar, has obtained my BTech Civil Engineering from Nagarjuna University in 1994, MTech Structural Engineering from JNTU Hyderabad in 2000, and PhD Structural Engineering from JNTU Hyderabad in 2009. Presently, I am working as Associate Professor in Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. My research areas include reinforced cement concrete designs, steel structural designs, structural analysis, point element analysis, earthquake engineering, bridge engineering, structural optimization. I have published 45 research papers in international as well as national journals and conferences, organized 3 international conferences and 11 national conferences as well as workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures, edited 2 books, supervising 14 PhD scholars and supervised 30 ME theses. Presently, I am actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 designs of reinforced concrete, steel, composite, low-rise, high-rise, multi-stored buildings and road as well as rail bridges. Right? Once we see the brief profile, student, let us move quickly to the top. The designs what we'll be seeing, right? This is how the type 1, this is how the unstiffened seated connection will be designing, right? Wherein we will design this seat angle, right? Wherein the same is now shown schematically, right? This angle will be designing, right? Will be designing using the welded connection, right? Now also will be also designing stiffened. This is what the stiffened seated connection, where we do have a stiffening a seat plate which is stiffened by a stiffener plate by means of the welded connection, right? This second design will be seeing, right? The same is shown now schematically, right? There is a to a column, a beam is connected by means of a seat plate which is stiffened by a stiffener at the bottom, right? And this is how in side view also, which are connected by means of the welds, right? These are the second design, student, right? Or even you can see the same in another schematic, right? That is how I have to have a seat plate, right? This is what the seat plate, and I have to have the stiffening plate or stiffener plate, which is connected by means of the welding, right? Fillet welding. Even we can provide a clip angle or cleat angle at the top to provide the stability, right? That is how the same is now shown in a 3D view, student, right? That is how this beam is connected to this column by means of the welding, as well as we do have a stability angle provided here by means of the bolts, right? Two bolts, right? Whereas at the bottom we can see that it is provided with this, right? Green color is what the seat plate, right? Seat plate which is stiffened by this stiffener plate, which is provided by this yellow, right? This stiffener plate is connected to the flange of the column by means of the fillet weld, right? That is how we'll see these designs. I hope you understood the designs what we are going to do. Now let us move quickly to the top. The first design, student, right? This design wherein I'll try to design the unstiffened seated connection, right? Unstiffened seated connection, right? Now wherein now the data is like this, right? Design an unstiffened seat connection or seated welded connection to join ISMB 350 514 Newton per meter with a column section ISHB 300 at 576.8 Newton per meter. The beam transmits an end reaction of 320 kilonewton due to factored loads. Use Fe410 grade steel and shop welding. Right now, to start with, we are designing it as an unstiffened seated connection, student. The same problem I'll also design using the stiffened seated connection also. The same data I'll use, right? Same data I'll use for stiffened seated connection also. Then you'll understand the difference of this stiffened as well as unstiffened seated welded connection, right? Now, whereas now let us see the given data, right? Fe410 grade steel is given, student. Therefore, the ultimate strength of this steel, right, is 410 Newton per mm square. And shop weld is given, therefore, from table 5 of IS 800 2007. I would have the partial safety factor gamma mw for the weld. This weld is equal to 1.25. And now if I go to SP61 1964, I'll go to table 1, page number 2. Then I'll note down the properties of this ISMB 514. What is that? Breadth of the flange, right? Now let me quickly go to that page number 2 of SP6, student, right? This is how I'm there in page number 2. Just bear for a moment, right? Yes, this is how ISMB 300, this is ISMB 350 514, ISMB 350 514, right? 514, right? And therefore I do have that ISMB 350 514 means 52.4 kg per meter. Therefore these are the relevant properties. The depth of the section is equal to 350 mm, the width of the flange is equal to 140 mm, and thickness of the flange is equal to 14.2, and thickness of the web is equal to 8.1. Like that, even if I go to the other data, right, the G, right, G means, right, the distance between the bolt center lines, right, or center lines of the holes of the bolt holes is equal to G. For this ISMB 350, it is 80 mm, right? Likewise, I'll also note down the properties for the column section from page number 4 for ISHB 300 576. ISHB 300, just let me go to that. ISHB 300 576, right? ISHB, this is ISHB 300 576, ISHB 300. Yes, this is that ISHB 300 at 58.8 kg per meter, or that 576.1. Therefore now I would have the depth of the section is equal to 300 mm, and width of the flange is equal to 250 mm, and thickness of the flange 10.6, and thickness of the web is equal to 7.6. Let us also see the gauge distance, right? I would have the gauge distance for this is equal to 140 mm. ISHB 300 gauge distance is equal to 140 mm. Therefore I just noted down these properties, student. Once I note down those properties, they are now given like this, right? All the relevant properties are written here, noted from SP61 1964, Indian Standard Special Publications 61 1964, right? Now once I note down that, then what I'll do is I'll go for the design of the seat angle. Therefore only we need to design the seat angle. That's it, right? Therefore let me go to that design of the seat angle, student, at a quicker pace, right? That is how now I'll initiate the design. Just bear for a moment, right? I'll initiate the design student, right? Before I initiate the design, let me go to that page number 79. I'll show the schematic also, right? That is how the schematic student, right? This is how, even in the previous video we have designed this for the same data. I have designed this as a stiffened seated connection student. You just revisit this, right? The same problem I have designed that as stiffened seated bolted connection, the same now I am designing as unstiffened seated welded connection. The same problem will also continue with the stiffened seated welded connection in today's class, right? Same is the data, right? This data just now we have seen, right? This relevant data just now we have seen and just noted from the SP61 student, right? For ISHB 300 as well as ISHB 350 as well as ISHB 300, that is how the schematics, right? These are the for the column, this beam is connected. If I see in the side view, that side view looks like this, right? This is the width of that flange of this beam, and the depth of this is equal to 350, and the width of this flange of this column is equal to 250 mm, right? And the thickness of this web is equal to 8.1 mm, and thickness of this flange of this beam is equal to 14.2 mm. This data just now we have seen, right? And this is how in plan view, right? The width of this flange of this column is equal to 250 mm, right? Whereas that of this width of this beam is equal to 140 mm, right? Therefore, I have shown all the three, one elevation, one side view, as well as that of the plan. Then you can visualize the 3D picture. I'll also show the 3D picture also, right? Now I'll also show the 3D picture, right? Whereas now I want to design the stiffener angle. Therefore, I do have this design student wherein let B be the bearing length of the I want to design the seat angle. I'm sorry, right? I want to design I'm there in the heading of design of the seat angle, right? Therefore, I want to design that. Therefore, let me go to that page number 107 student, right? Wherein, right, I'm designing this first part, right? I'm designing this first part wherein design of seat angle, right? Therefore, let me go to that same design student, right? Therefore, I'm just initiating that very first step. I'm starting the design of the seat angle, right? This is that design of seat angle, right? Wherein now I want to find out what is that bearing length required, right? Therefore, let B be the bearing length of the seat angle required. Therefore, I know that formula that the reaction from the beam R is equal to the permissible stress. Permissible stress is equal to 250 divided by 1.1 in this steel member, that multiplied by that bearing area required, right? That is how the bearing area required is equal to B multiplied by this thickness of this web, 8.1. Therefore, that is how. Now, what is this bearing length required? Now, I'll get this bearing length required is equal to, say, 173.82 mm required. Whereas I'll provide a gap of 5 mm between the end of the flange and that of the end of the beam. This much of 5 mm gap I'll provide, so that it will safeguard during expansion and contraction. Therefore, now total length of that bearing length required is equal to 173.82 plus 5. Our side is 178.8. 178.8 is the bearing length required. Or let us say I want to provide 200 mm. I want to provide 200 mm like this, right? Therefore, this I want to provide bearing length as 200 mm, right? Then, however, just now we have seen that the thickness of what should be the thickness, right? However, just now we have seen the thickness of the beam. This beam is equal to 8.1 mm. Therefore, the thickness of this angle should not be less than 8.1 mm, right? Should not be less than 8.1 mm. Otherwise, it cannot bear that load. It cannot bear that load. It will fail in that bearing or load transfer criteria, right? In bearing criteria, right? Therefore, I do have the angles as, say, now 200 is already fixed. Therefore, with that, now I do have either 100 mm or 150 or 200 mm. Therefore, now what I'll do is I'll proceed with an unequal angle or equal angle sections, out of which now in order to optimize the section, I'll proceed with unequal angle, right? This 150 mm. Therefore, now I'll take ISA 200 by 150, 200, right? 200 by 150, and I do have, for this angle, I do have the thicknesses, right? 10 mm, 12 mm, 15 mm, 8 mm are available. However, the thickness should not be less than 8.1 mm student. Therefore, I'll simply proceed with that of the first thickness, right? T is equal to 10 mm. 10 mm. That is how I'm saying that. Hence, provide an angle, the seat angle of 200 by 150 by 10 mm to transfer this load of 320 kilonewton, 320 kilonewton safely, right? That is how the design. And you also connect the flange of the beam by means of 224 mm dia bolts, right? So that the beam will have a perfect contact, and it will not move here and there due to the application of the load, right? That is how just two nominal 224 mm dia bolts. Now like this, right? Now let me go to this further design student. Now I want to design the first component is over. Now I want to design the welding, right? Now next heading is the design of the welding. This part just now we have concluded that design of the seat angle. We have concluded that yes, I want to provide ISA 200 by 150 by 10 mm seat angle, and also provide a nominal flange cleat angle of ISA 100 by 75 by 8 mm with 5 mm nominal 5 mm size weld. I'll show that schematically, right? Now let us move to the second component design as design of the weld student. I do have this formula reaction R is equal to permissible shear stress in the weld Fu divided by root 3 multiplied by partial safety factor 1.25, that multiplied by the weld area, right? Weld area in this shearing criteria. Therefore, length of that weld multiplied by the size, right? Therefore, now I do have this substituting with, now I'll get what is that size, right? What is that size, right? Therefore, 320 multiplied by 10 to the power 3, 320 multiplied by 10 to the power 3, Fu 410 divided by root 3 multiplied by 1.25. That multiplied by length of the weld multiplied by effective throat thickness, not the size, student, right? Effective throat thickness, right? Effective throat thickness. Therefore, now I'll get the effective throat thickness required is equal to 5.63. Therefore, if effective throat thickness is equal to 5.63, then that multiplied by root 2 is the size, right? Therefore, now it works out, say approximately say some 7 point odd value, right? Or say 8 mm, right? However, even now let me check what should the minimum size of this weld, right? Therefore, if I see the welding is done between the components of the thickness 10 mm, that of this seat angle thickness is equal to 10 mm, as well as the thickness of the flange of the column is equal to 14.2 Out of this, whichever is maximum, 14.2 is the maximum. Therefore, if I go to this IS 800 2007, table 21, page 78. Let me go to that page 78, student, at a quicker pace. Page 78. Now I'm there in that page number 78. Therefore, there the minimum size from this table 21 is 5 mm, right? However, already I got root 2 multiplied by 5.63, approximately some 7 point odd value, or say 8 mm, right? Therefore, we already got roughly greater than 5 mm. Therefore, provide 8 mm. Therefore, provide 8 mm fillet weld along the connected leg of the angle with the column flange, and also provide say 6 mm size weld connecting toe of the outstanding leg of the angle with that of the beam flange. Now I'll show that schematically like this, right? Just bear for a moment, right? Therefore, I'm showing that schematically like this, right? Therefore, just now I have proposed the design. I got this length, right? This length as say 200 by 150, 200 by 150 like this, right? Let me show that schematically once again. 200 by or let me show that schematically also like this, right? That angle, I'll show that angle separately, right? That is how I just provided 200 by depth 150 mm, right? Whereas its width is equal to 140 mm, that of this angle, right? Seat angle, right? And now you can see the size 200 mm by 150 mm, 200 mm by 150 mm, whereas its width is equal to 140 mm, like this, 140 mm, right? Now I'm showing all the three, the front view as well as the side view, right? And I've just taken out this seat angle, right? That we also I'm showing with this thickness. Now I'm showing that same in the 3D view, right? 3D view. Now that 3D view is like this, right? Therefore, that is I've just taken out that 3D view, right? Therefore, I do have this leg, right, as a 200 mm, and this connected leg to the flange of this column as 150 mm, right? 150 mm. Therefore, 200 and 150 mm like this, right? This is 200 mm and this is 150 mm, which is connected to the flange of this column. And just now we have designed, I got this weld size as say root 2 multiplied by that 5.46 or say 8 mm, right? This, right? And also I have to have a beam provided here. Let me show this, right? Like this, right? Just now, right? This is 200 mm, this is 150 mm, student, right? Therefore, now what I am saying is this 150 mm, right? Whereas also provide a weld of 6 mm connecting this toe to that of the flange of the beam, or if you don't want to do that, you just provide 224 mm dia bolts. Let us say you don't want to do this welding here to the toe of the angle, to the toe of this angle connected to the bottom of the flange, bottom of this flange, like this, right? If you don't want to do this welding, here using 6 mm, you provide 224 mm dia bolts in two rows, like this, right? Therefore, in two rows, right? Therefore, either of the two is true, right? Therefore, that is how the schematic, student. I hope you understood the design of unstiffened seated connection, unstiffened seated welded connection. Now, if you understood that, now let us move quickly to the next design, student, right? Next design is that of the design, right? This is a design of a stiffened seated connection, stiffened seated welded connection. Therefore, the same is the data as if that of the previous problem, student, right? Even the same was the data for the design of the stiffened seated bolted connection, right? Stiffened seated bolted connection, same is the data. I'm not changing that data for all the three problems. The data is same, right? However, now I'm designing it as a stiffened seated welded connection, right? Design a stiffened seated welded connection to join ISMB 350 at 540 Newton per meter with a column section of ISHB 300 at 576.8 Newton per meter. The beam transmits an end reaction of 320 kilonewton due to factored loads. Therefore, use Fe410 grade steel as well as the shop welding. This data we already seen in the previous problem also, student, right? Therefore, that is a given data. Fu for the steel is equal to 410 Newton per square and shop weld gamma mw is equal to 1.25, and just now we have seen from SP61 this data for ISME 350 at 540 Newton per meter. I have this breadth of the flange 140 mm, thickness of the flange 14.2, and thickness of the web 8.1, and gauge distance G is equal to 80 mm, as well as for ISHB 300 at 576.8 Newton per meter. Breadth of the flange is equal to 250 mm, and thickness of the flange is equal to 10.6, and thickness of the web is equal to 7.1, and gauge distance is equal to 140 mm. We have seen that in the previous problem. I'm just recalling that. Now, first design is the design of the seat plate. Let me show this design, student. What I'm trying to do is this one, right? This is how I want to design this first seat plate, followed by the stiffener plate or stiffener plate, right? These two designs I want to do, along with the third component is that the third one is the design of this weld, right? Let me also show this another using another schematic, student, right? This seat plate I want to design first, right? This seat plate, right? Then next component I want to design this stiffener plate, right? Then third one is I want to design this fillet weld. Therefore, these three designs we'll see, right? Or this is how, right? First, we'll see the design of the seat plate, followed by the stiffening plate, followed by the design of this fillet weld. Three components, right? Therefore, now let us see this first component as that of the design of the seat plate. Therefore, let B be the bearing length of the seat plate required. Even in the previous problem also I explained that elaborately, right? Therefore, now there also I required 173.82. Therefore, R is equal to F divided by gamma m naught. B multiplied by thickness of the web 320 into 10 to the power 3 is equal to 250 divided by 1.1. B multiplied by 8.1. Therefore, this is the same result as if that of the same previous problem, 173.82. Even we have assumed 5 mm clearance between the beam and the flange, like this, right? This is the 5 mm gap. Student, right? Therefore, if you have R, this is that gap, right? R, this is that gap exactly, right? 5 mm gap, right? So that it will permit the expansion and contractions, right? Then once we see that gap, therefore the breadth required is equal to 173.82 plus 5 mm. It works out 178.82. Even the previous problem also it was same, but we have provided 200 mm. But now I'm restricting to 180 mm. Now in this problem I'm restricting it to 180 mm. And also the next one is that width should be greater than that of the breadth of the flange, which is 140 mm. Now let us see. Therefore that width required should be greater than the breadth of the flange of the beam, student. Please make a note, right? That of the width of the flange of that beam, right? So that it will have a perfect bearing, right? If it is less than that width of this, beam flange width, then stress concentration will come into picture. At least it should be greater than, or at least equal. It is equal to. Otherwise, right? Therefore, please remember, student, right? Don't do mistake here, right? Therefore, I'm saying because width of that flange is equal to already 140 mm. I'm saying 10 plus 10 extra, so that 10 mm will be extra here, right? On either side, right? This is a 10 mm extra here, right? 10 mm extra and 10 mm extra here, so that this will have perfect load transfer onto that seat plate, onto this seat plate, right? Onto this seat plate, student, like this, right? Therefore, Now I am fixing it as 160 mm, therefore it is okay. And what should be the thickness? Thickness should not be less than the thickness of the flange of this beam. However, that is equal to 14.2, therefore R say 16 mm, therefore it is okay. Therefore hence provide a seat plate of 180 mm, right, 180 mm by 160 mm by 160 mm by 16 mm. Let me show this, right? I'll show that schematically. Therefore this is how my 180 mm, 180 mm, right? This is that 180 mm, student. I'm showing this, right? 180 mm by 160, right? This dimension is equal to 180 mm, right? 180 mm. Whereas if I just see, right, perpendicular dimension, right, this dimension is equal to 160 mm, whereas this bearing length is equal to 180 mm, 180 mm, and its thickness is equal to 16 mm, right? That is how I'm showing in front elevation. The same is also seen in side view, right? That is how this width in side view is equal to 160 mm, right? That of this seat plate, right, 160 mm, and its thickness is also seen as 16 mm. I hope you understood the design of this seat plate. Now let us move quickly to that of the design of this stiffener plate, right? This stiffener plate, white part, right? Whereas the black part is that of the fillet weld, right, on either side, right? Now let us do that second design, student, right? The second design is design of stiffener plate, right? Now I want to design that. Therefore just now I have shown schematically how that looks, right? Therefore here the thickness of the stiffener plate shall not be less than the thickness of the web of the beam. However, that is equal to 8.1 mm. Let us say, let's provide 16 mm thick stiffener plate, student, right? And the distance of end reaction from the outer edge of the seat plate, right? Just now I have provided 180 mm, but in the calculation I got 178.82. However, I provided that as 180. Therefore 180 actual required is equal to only 178.82, including that of the 5 mm gap, right? Therefore now the difference of these two will now work out 90.59 is the distance of the end reaction from outer edge of that seat plate, Therefore now the bending moment, right, is equal to M is equal to P multiplied by E, 320 10 to the power 3 multiplied by E, 90.59 eccentricity, that divided by 10 to the power 6, or say 28.99 kilonewton meter, right, or multiplied by 10 to the power 6 Newton mm. Now the depth of this stiffener plate can be determined from buckling criteria, right? From buckling criteria like this, right? And therefore, if I if I provide like this, then obviously it may buckle, right? Therefore, that will govern the design. Therefore, now if I go to this table 2 of IIC 800, page number 18. Let me go to that page number 18, student, at a quicker pace. IIC 800, page number 18. Therefore I am there in that page number 18, student. Therefore almost now this is how the stem of T section are rolled or cut from a rolled I or H section. However, the section what we are now designing is looking like a T section, right? Because a seat plate along with that of this stiffener plate looks like as if a T section. Please see this, student, right? Therefore now this stem of the T section is applicable. Therefore there I do have for this class 3 semi-compact from table 2, limiting width to thickness ratio from IS 800 2007, right? Therefore there for this semi-compact I do have 18.9 epsilon, where epsilon is equal to square root of 250 divided by 250, because the yield stress of this steel section is 250. Therefore epsilon is equal to 1. Therefore substituting which, now I have to have for this semi-compact d by t should be less than or equal to 18.9 multiplied by 1. Therefore d by t should be less than 18.9. Therefore this depth of this stiffener plate should be less than 18.9 multiplied by its thickness 16 mm. Therefore it should be less than 302.4. This depth should be less than 302.4, or say let us provide this depth as 300 mm, so that it will not buckle, right? Therefore then, and also the width of the stiffener plate, this width of the stiffener plate should be equal to the width of the seat plate. Now I'll show that, right? Is equal to 180 mm. Therefore provide a stiffener plate of 300 mm depth, right, and its width is equal to 180 mm by 16 mm thick. Now I'll show schematically, right? Let me go to that and let me show that stiffener plate, 300 by 180, right? This is how, right? 300 is the depth, 300 is the depth, or even you can see here 300 mm is seen the depth, right? And this width 180 mm itself is equal to the width of the seat plate. Otherwise there will not be any bearing, like this, right? If you provide less, then obviously stress concentration will occur. Therefore this is how the seat plate, therefore its width should also be matching with that same value, therefore 180, right? Therefore that is how this 180 mm, right? 180 mm is this along x-axis, right? Along y-axis the depth is equal to 300 mm, just now we have designed, and its thickness is equal to 16 mm. This is how the design of stiffener plate, right? Even now we can see in side view the thickness 16 mm is seen, and its depth is equal to seen as 300 mm, that of this stiffener plate, right? Let me show this schematically, student, right? Like this, right? Like this, right? This is 180 mm, this depth is equal to 300 mm, and this thickness is equal to 16 mm, right? This depth is equal to 300 mm, right? 300 mm, and this width is equal to 180 mm, and thickness is equal to 16 mm. Or let me also go to another schematic, student, right? Like this, right? This schematic just now we have seen, right? Like this, right? Therefore this is 180 mm, this depth is equal to 300 mm, that of this stiffening plate, and this thickness is equal to 16 mm, right? Once you understood that, now we'll go to the design of the third component. The third component is the design of the weld. Now this weld is only pending, right? That of the fillet weld, which is provided on either side of this stiffener plate, either side of the stiffener plate, and also connecting the seat plate, right? Now these designs will now do, right? Therefore third component is the design of the weld, right? And therefore the weld is provided in 2 rows, as I have just now shown, like this, right? Weld is provided on either side of this stiffener plate in 2 rows, like this, students, right? In 2 rows, right? In 2 rows. Therefore that is how this is the 16 mm thick plate, stiffener plate. This is how one weld, another weld in 2 rows, right? Or in front view it is looking like this, right? Therefore now I'll find out the CG of the group of the weld from bottom of this seat plate, right? This is how from this bottom of this seat plate I'll find out, right? With respect to this bottom of this seat plate. Therefore however this horizontal weld, that itself is matching with the bottom, therefore its perpendicular distance is equal to 0. Therefore that one multiplied by that width of this horizontal weld is equal to 160 minus 16 mm. That 16 mm will be considered in 300 mm depth, right there. Therefore that, however, it is a CG is at a distance of 0 mm, right? However, next that of the 2 vertical welds of depth 300 mm, 2 multiplied by 300 mm, whereas it is a CG is at a distance of 150 mm. That divided by the area of these welds, right? 2 vertical welds 300 mm depth and one horizontal weld of 144 mm, right? Therefore that is however these are the lengths only, student, right? However, that multiplied by effective throat thickness in the numerator as well as in the denominator. However, that in the numerator as well as denominator, that effective throat thickness gets cancelled. Therefore, I do have that CG of the group of the weld is equal to 120.96. However, you please see that that extreme fiber is in tension, right? Whereas the remaining distance y2 bar is equal to 300 minus 120.96 is equal to 179.04. Let TT be the effective throat thickness. Let me show this y1, right? This is how y1. Just now I got from solving this, I got y1 is equal to 120.96 and y2 is equal to approximately 179. This distance, right? And therefore, this is this extreme fiber is in tension, whereas this extreme fiber is in compression, right? About this neutral axis, right? Right? Therefore, now once I know the CG distances, student, let TT be the effective throat thickness, right? However, they cancelled in numerator and denominator. Now next subheading is the moment of inertia, right? The moment of inertia about the centroidal XX axis of the group of the weld, student, please make a note, right? Is equal to that of this horizontal weld, one horizontal weld of 144 multiplied by effective throat thickness, right? And the distance from the CG is 120.96 AH square, right? H square is equal to 120.96. That of the horizontal weld is over, and that of the two vertical welds like this, right? Therefore, two vertical welds are there whose effective throat thickness is equal to TT and depths are 300 mm and 300 mm like this, right? Therefore, B is equal to TT multiplied by 300 mm cubed by 12. Sorry, BT cubed by 12. Sorry, there is a writing error. BT cubed by 12 multiplied by, using parallel axis theorem, AH square. What is that? Area of each of these is equal to 300 multiplied by effective throat thickness, right? That multiplied by H square, perpendicular distance is 179.04 minus 150. Therefore, 29.04 from the CG of the XX axis to that of the CG of this vertical weld. Its CG is there at a distance of 150. Therefore, the difference is equal to 29.04. There are two such vertical welds, therefore outside 2, right? Therefore, it now works out 262.41 in 10 to the power 4 multiplied by TT, effective throat thickness, multiplied by effective throat thickness, mm to the power 4, right? Once I get this, student, then now I'll calculate the direct shear stress or vertical shear stress. Q1 is equal to the vertical shear force VU in this weld, that divided by the shearing area of these welds, vertical welds as well as that of the horizontal welds like this, right? Therefore, I do have 320 kilonewton shear force, factored shear force, that divided by two vertical welds of 2 multiplied by 300 multiplied by effective throat thickness, and one horizontal 144 multiplied by effective throat thickness. This is how the denominator, that effective area of these welds, that of the horizontal and two vertical welds. Therefore, doing which now I'll get 430.1 divided by effective throat thickness TT, Newton per mm square. Similarly, the horizontal shear stress due to bending moment in extreme tension fiber, right? That extreme tension fiber, just now we have seen that is at a distance of 120 mm from neutral axis, at a distance of 120 mm, because of that load, this will be under tension like this. This weld will be under tension, student, right? Therefore, which is there at a distance of 120.96. Therefore, m is equal to we have already calculated 28.9 and 10 to the power 6 multiplied by 120.96 divided by IXX 262.41 10 to the power 4 multiplied by TT in the denominator. It works out, say, 1336 0.26 divided by effective throat thickness, Newton per mm square, right? Once I get that, however, you please see that even this bending, due to that bending also, right? This the stiffener plate is subjected to bending. However, the weld which is connected to that is shearing. That bending moment in the stiffener plate is leading to shearing, like this, right? It will shear the weld or the group of the weld. Therefore, that bending moment in the stiffener plate is leading to the shearing stress in the group of the weld. Therefore, it is now under one direct shear stress, right? And second one which is horizontal, right? One is direct shear stress acting in the vertical direction. The second one is due to tension which is acting in the horizontal direction, right? This is how the horizontal shear stress due to bending movement, right? Which is Q2, right? Therefore, what is the resultant of these two, right? Square root of Q1 square plus Q2 square. Therefore, now it works out, say, substituting the numeric values, now it works out the resultant shear stress as 1403.77 divided by TT, effective throat thickness, Newton per mm square. However, we already know, even in the previous problem we have seen, as per IS 800 2007 class 10.5.7.1.1 page number 79, that permissible shear stress of the weld is equal to Fu divided by root 3 gamma mw. Let me go to that page number 79, student, right? 79, yes, 79. Yes, I am there in that page number 79, student, right? Therefore, this is that formula, right? FWD is equal to FWN divided by gamma mw, where FWN is equal to Fu divided by root 3. Therefore, substituting which, now I'll get this result as a 410 divided by root 3 multiplied by 1.25, it works out 189.37. The permissible shear stress in the weld is only 189.37, but the actual shear stress due to the resultant of these horizontal as well as vertical stress is 1403.77 divided by TT, Newton per mm square. However, that should be less than or equal to the permissible shear stress of 187.37 Newton per mm square. Therefore, solving which, now I'll get effective throat thickness should be greater than or equal to 7.41 mm. Right? Therefore, what is the size of the weld? Size of the weld is equal to root 2 multiplied by 7.41. It works out, say, 10.48 mm. However, we are connecting this weld between this 16 mm as well as that of, right, this 16 mm as well as that of the another connection is that of this 16 mm, that of the seat plate 16 mm, that of the stiffener plate is also 16 mm, or that of the thickness of the flange, this thickness of this flange of this column, right? Therefore, that is equal to 10.6, right? Therefore, out of these, whichever is minimum, 16 mm is the minimum. Therefore, what now I'll do is for 16 mm from table 21 from page number 78, what is the minimum size? Now let me see that minimum size of this weld, right? And that is how that minimum size for 10 to 20 mm, 16 mm, 5 mm. However, I already got from design more value, more result, right? Therefore, now I'll provide that value, or say, right? Therefore, I got already from design 10.48 is the size, right? Therefore, or you say provide, or say 11 mm. Therefore, that is why I am providing this 11 mm this horizontal weld as well as this vertical 2 rows as well as at the bottom, even at the bottom it is acting as if the end return, right? That is how horizontal weld which is connecting the seat plate to the top of the stiffener plate as well as the stiffener plate is also connected by means of two vertical welds of 11 mm thick, 11 mm size, 11 mm size, right? That is how the design, and its depth is 300 mm, right? That is how the, and also let us provide a nominal size flange cleat angle ISA 100 by 100 by 6 mm, connected by means of 5 mm fillet weld, connecting the toe of this angle connecting to the flange of the beam, as well as connecting this toe of this angle to connecting that of the flange of this column as shown in this figure, right? That is how the figure, student. I hope you understood this discussion. Let me show this in a right. This is how just now we have designed, student. Let me show this in a 3D view, right? That is how this beam ISMB 350, which was connected to IS HB 300, right? It was resting on a seat plate, which is shown here in the green color, right? And that in turn is stiffened by this stiffener plate, right? Just now we have seen this design, right? Therefore provide 11 mm fillet weld in one row. On the other side it is not seen, right? Even in other row as well as horizontally, right? Even at the bottom you can see this yellow horizontal, right? 11 mm. That is how the 3D view of this design also, right? Okay, student, I hope you understood the discussions what we had in today's class, right? If you have really enjoyed the discussions what we had in today's class, right, you don't forget to click subscribe and share to our YouTube channel, right? We'll meet in the next class with design of tension members, a new chapter, right? Design of tension members, a new chapter. There we'll see the codal provisions and as well as the theory pertaining to it, what are the different sections, what are the advantage and disadvantage and sections also, right? We'll meet in the next class with this tension member designs. Till then, bye bye students.